Section 3 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 2. The Evolution of Astronomical Methods of Observation. Part 2. By using a small Gregorian telescope, Herschel had his attention directed to the wonders of astronomy. His income being too limited to purchase an instrument, he set about making one for himself. During his life he is said to have made upward of 400 telescopes, mostly of the Newtonian type. Among his earliest efforts was the construction of a 5-foot reflector, which was a wonderful success. Then came one 7 feet in length. The largest of his instruments was completed under George III in 1789. This telescope surpassed all his previous efforts, for it was actually 40 feet long and had a reflecting mirror 4 feet in diameter. The story of Herschel's work with this great telescope would fill a volume. The largest telescope of the reflecting type was constructed by Lord Rosse, an Irish peer, and used at Parsonstown. It had a mirror of 54 feet focus and a diameter of 6 feet, but it could be used only for observations on or near the meridian. While out of use for many years, it long held the record for size, which, however, is now taken by the 100-inch reflector recently completed for the Mount Wilson Solar Observatory, California. The case of the reflecting telescope, which, as we have seen, had been all but abandoned on account of its chromatic aberration by the 17th century astronomers and physicists, was not as hopeless as they believed. Notwithstanding Newton's dictum that it was useless to try to improve it, owing to the impossibility of producing refraction without dispersion, Euler read a paper before the Berlin Academy in 1746, proving mathematically the possibility of correcting both the spherical and chromatic aberration of an object glass. Upon reading Klingenstirner's paper corroborating Euler's views, John Dolland made a series of most valuable experiments which led him to the solution of the problem of the achromatic object glass, namely, that by properly combining two kinds of glass, flint and crown, he could unite the colored rays fairly well and still have refraction to unite the incident rays to form an image. Dolland's discovery occurred in 1758. His work soon became famous. He was surely master of his subject and had a clear field for many years. Like other opticians, he labored under great difficulties in securing glass suitable for telescopes of any diameter. Fortunately, a genius had taken hold of this problem in the person of Guinand, a Swiss watchmaker, who, after long experimenting, solved the problem of making fine discs of optical glass. He associated himself with the celebrated Fraunhofer in 1805, and they successfully made optical glass discs up to 15 inches aperture. To Fraunhofer are due many of the most important discoveries in the theory of the achromatic objective. With proper optical glass and methods of correction, the refracting telescope soon came into its own. The size of the objectives was increased so that sufficient amounts of light were gathered to form a distinct image. The best makers of Europe gradually developed both lenses and mountings, so that precision of measurement and ease of adjustment were secured. It was in the United States that the best work in this field began to be carried on. The lenses of Alvan Clark gained an international reputation. An objective 30 inches in diameter was made by him for the Russian observatory at Pulkowa, soon after a 26-inch telescope had been completed for the U.S. Naval Observatory in Washington. These were succeeded by the 36-inch instrument of the Lick Observatory and the 40-inch telescope of the Yerkes Observatory, with both of which results in proportion to their increased size have been obtained. The 17th century really marks the beginning of instrumental work and accurate measurements in astronomy. The vernier, which made it possible to subdivide linear and circular scales with accuracy, made its appearance in 1631. In 1640 the optical axis or line of direction of the telescope was practically defined, and the micrometer was invented by William Gascoigne (1612 1644), which was the forerunner of the filar micrometer, so essential to modern astronomy, where an image at the focus of a telescope can be measured. The micrometer is indeed an important adjunct to the telescope, for, unless angular distances can be measured, the mere bringing nearer of the celestial bodies would have but a limited amount of usefulness. In the micrometer of William Gascoigne, two pointers carried by a single screw were placed at the focus of a telescope. When these pointers were parallel, they pointed to zero. But by revolving the screw they could be separated, and the number of revolutions or parts of a revolution could be read from a divided head. Consequently, all that it was necessary to know was the distance between two successive threads of the screw, in order to obtain an exact value for any distance which the pointers might separate. Now, if it were desirable to determine the angular distance between two stars, each pointer was set on a star, and the distance between them was thus gradually measured, so that by simple mathematics the corresponding angular distance could be computed. Micrometers soon became an important part of exact observation with a telescope. Auzout and Picard made subsequent improvements, so that finally a micrometer resulted in which a spider filament was placed on a frame moved by a screw with graduated head, thus enabling increased precision of observation to be obtained. This is the fundamental device now used with various improvements and refinements. Römer, who was the first to determine the velocity of light, improved the micrometer in 1672 by adding springs to take up the lost motion. He also constructed the first meridian telescope in 1689. By the middle of the 17th century the use of telescopic sights for determining the position of the stars had become established. The precision of the observations of that epoch may be estimated at 10 seconds of arc, which corresponds to the diameter of a lead pencil seen at a distance of about 550 feet. Methods and instruments continued to improve. The observations of Lalande attained a limit of precision of 1 second of arc, corresponding to a pencil at 5,500 feet. At the beginning of the 19th century great improvements were made. In 1875 the limit of precision had been reduced to 1/2 a second, which removes the lead pencil to 11,000 feet, or more than 2 miles. For minute measurements one of the most useful devices has been the heliometer or divided object glass micrometer, the first really available type of which was constructed by Fraunhofer for the observatory at Königsberg. In this instrument an object glass or lens is used, which is divided along its diameter. The two parts of the glass are mounted so that they can be moved laterally with respect to each other. Consequently each half supplies a distinct image of the same object, but separated by a strictly measurable amount. Thus, if a double star is under examination, the two half lenses into which the object glass is divided can be moved until the upper star in one image is brought into coincidence with the other star in the lower image, so that the distance apart becomes known by the amount of motion employed. By using screws with heads of considerable size to move the halves of the object glass, the heliometer can be read to the 1,000th part of a revolution, and in the case of the Königsberg instrument such a division, equivalent to 1/20th of a second of arc, could be measured with accuracy. This new instrument, which was not mounted until 1829, 3 years after the death of Fraunhofer, was at once employed by Bessel to solve the problem of star distances. His measurement of the parallax of the star known as 61 Cygni, corresponding with a distance about 600 times that of the Earth from the Sun, not only was considered ascertained beyond question, but is spoken of by Miss Clerke as "memorable as the first published instance of the fathom line so industriously thrown into celestial space, having really and indubitably touched bottom." In 1874 the heliometer was applied to the observation of the transit of Venus, and again in 1877, when Mars came into opposition with the Sun, Sir David Gill, using the heliometer, made a valuable determination of the solar parallax, obtaining a value of 8.78 seconds, corresponding with a distance of 93,080,000 miles. By this time the heliometer had become an accepted method for improving astronomers' knowledge of the Sun's distance. A number of heliometers were employed in cooperation at different points of the Earth's surface, the work of Professor Elkins at Yale in connection with Sir David Gill at the Cape of Good Hope Observatory being especially notable. Another modern development of telescopic astronomy has been the direct measurement of the magnitude and brightness of a star, thus superseding to a great degree the judgment of the eye upon which the older astronomers had depended from the days of Hipparchus. The photometers, light measurers, used with telescope for this purpose consist either of those designed to cut down the amount of light furnished by a measurable amount and thus cause the star to disappear, or those in which conditions are so arranged that the light of the star appears just equal to some standard light. Under the first head is the so-called cat's eye, in which a wedge of dark neutral tinted glass is placed close to the eye, either at the eyeball of the eyepiece or at the principal focus where the micrometer wires are usually placed. As the wedge is introduced until the star just disappears, the graduation is read, which graduation can be reduced to a scale of magnitudes. In the other class of photometers the light of the star is compared with an arbitrary artificial star formed by light from an oil lamp shining through a small aperture. To Huygens is due the application in 1655 of the pendulum to the practical measurement of time, thus giving us a clock so regulated that it was possible to make accurate time observation. The invention of the pendulum clock, patented in 1657, therefore marks a distinct epoch in astronomy. The most usual and most useful form of mounting for a telescope is the equatorial, the principal axis of which is inclined at an angle equal to the latitude of the observatory, and is directed toward the North Pole in the northern hemisphere and toward the South Pole in the southern hemisphere. The axis of the instrument is thus parallel to the Earth's axis of rotation, and is therefore called the polar axis. It carries a graduated circle which is parallel to the celestial equator, known as the hour circle, from which circle may be read the hour angle of the body upon which the telescope happens to be pointed. The polar axis also carries the bearings of the declination axis, which is perpendicular to the polar axis and carries the telescope itself and the declination circle. When the equatorial telescope is directed toward a star or a planet, it is necessary only to use clockwork machinery to cause the polar axis of the instrument to turn with a uniform motion in order to follow any star or planet which otherwise would soon be carried out of the field of view by the rotation of the Earth. The equatorial also enables the observer to look at once to a particular part of the heavens where a given body is expected to be at a given time. The mounting for a modern equatorial telescope requires large and heavy moving parts. Where a solar or stellar image is desired, it does not seem desirable to employ such a heavy mechanism. To Léon Foucault, about 1868, the idea occurred to construct a fixed telescope with a mirror, moving with 1/2 the angular velocity of the sun, deflecting a beam in a fixed direction. Such an instrument was constructed and was employed with good results, although its operation was marred by imperfections in its driving mechanism. However, the device did not attract much attention until plans were made in the eclipse expedition of 1890 for extensive photographs of the phenomenon. It was proposed to use the instrument in connection with a second mirror to produce an image which would not move. This device, now called a ccelostat, was found admirable for eclipse photography. Experiments were made at the Yerkes Observatory to construct such an instrument for solar work. The work was subsequently transferred to the Carnegie Institution Observatory on Mount Wilson. An extension of the same principle may be found in the tower telescope of that institution, where a ccelostat is mounted on the top of a skeleton tower, and a beam of light is reflected to a laboratory beneath. Today the most modern and efficient reflecting telescope of large size is the 100-inch instrument designed for the same observatory by Professor G. W. Ritchie. At the present time both refracting and reflecting telescopes are in use and have been brought to a great degree of perfection. Just which is the better it would be hard to say. The old speculum metal reflector has been almost discarded, and glass, coated with silver, has been substituted. The glass is much superior to the metal, as it can be figured more accurately, and if tarnished the silver can be removed without changing the figure of the mirror. Again, much study has been given in France to a form of telescope known as the equatorial coudé, in which the optical axis of the telescope is parallel to the axis of the Earth, and the light of the star is reflected into it by two mirrors. Such an instrument, constructed for the Paris Observatory, has been very convenient for the astronomer, who can sit in his chair and observe the stars as easily as he can use his microscope. But the loss of light and definition by the double reflection, as well as the deflection of the mirrors and the varying temperatures to which the different parts of the instrument are subjected, render this construction far from perfect. End of section 3.